his master degree in 2002 in chemistry from Nauroji Wadia College, Pune, which is affiliated to Savitribai Phule, Pune University. Dr. Sudhir Arbus sir completed his Ph.D. degree in photocatalysis from Department of Chemistry from Savitribai Phule, Pune University. Sir also work in National Chemical Laboratory, Pune and Bhabha Atomic Research Center, Mumbai. His area of research is nanomaterial synthesis, photocatalysis, hybrid solar cell, and hydrogen storage. Dr. Sudhir Sir published 92 research papers in international journal and attend several national and international conferences. He also served as a guest editor for American Scientific Publisher Journal. Dr. Sudhir Arbuj is fellow of Maratha Academy of Science. He has guided 5 PhD students and 1 MPhil student and more than 76 MSc students. So everyone, please join me in welcoming Dr. Sudhir Arbus sir for his guest lecture. Sir, I kindly request you to please log in your lecture. Thanks you and all.
Thank you.
Thank you.
Thank you, Yogita, for nice introduction. So just confirm me two things. My voice is audible to all of you.
Yes, sir, you are audible.
My slides are moving.
Yes, sir.
Okay, now we'll start our lecture.
Okay, sir.
First of all, let me say thanks to Professor Satish Ahire and Principal Jagdale sir for giving me opportunity to give some lectures at this PhD coursework at LBH. So today I'm going to speak about UV visible absorption spectroscopy in first lecture, and second lecture I will talk about the photoluminescence spectroscopy. So this is the content of my presentation. So in this first, I will introduce about what is meant by spectroscopies, then few basic things, electromagnetic radiation, what is molecular orbital theory, then the main principle for different electronic transition, then the backbone of our visible spectroscopy, the famous Lambert's law, Beer's law, and combined Lambert-Beer's law. Then I will cover some instrumentation part also, what kind of light source, then what kind of monochromators, detectors, display. And the last important part, application. What is the application of this invisible spectroscopy in our day-to-day life, as well as the main focus, what kind of research work we are doing, and what is the useful of this invisible spectroscopy in our material-related point of view or material applications. So in that few applications, I am covering qualitative as well as quantitative application, then how to find out the band gap of the material. And later on, I will discuss about the few results, my own results that I have analyzed with the usable spectroscopy and how this usable spectroscopy is useful for our research. So before going to the presentation, so let me tell you about what is meant by CMET and what exactly this organization is. So I think in last lecture, Dr. Goin must have given you some idea. So CMET stands for Center for Material for Electronics Technology. The name itself defines what we are doing. We are developing the materials that are being used to develop different kind of electronic components. So we have 3 laboratories, CMET Pune, CMET Hyderabad, and CMET Thrissur. So CMET comes under the Ministry of Electronics Information Technology. In short, it is MIT. So this CMET Pune is lab as well as headquarters. Each lab has independent director, and we have director general who monitors the activity of all 3 CMET labs. So in short, CMET Pune is working in the area of nanomaterials, then lithium-ion battery, low temperature core-fired ceramics, additive manufacturing, and then recently 3 years back, a new project started, quantum computing, 2D materials for quantum computing. So one of our group is developing 2D materials. Then Hyderabad laboratory is well known for designing the high purity materials like 7N purity or 10N purity or 13N purity materials. Like 7N means 99.999, 7N, 13N 99.99. They are working on silicon carbide materials, ROHS materials. Then CMET Thrissur, they are working on micro substrate materials, micro absorbing materials. So each lab has our own mandate. As per their mandate, they are working in the specific areas. Okay, that's all about our CMET. Now we'll go to our today's main Uh, okay, this one, I thought we should discuss about this slide at the beginning only. How to get opportunity to work at CMET. Okay. Generally, in CMET, we are recruiting BSc or MSc students with specialization in physics, chemistry, and electronic science. We are also hiring BE in E&DC or chemical engineering, MTech nanotechnology. Then CMET is affiliated to Savitribai Phule Pune University for research work. So we are providing PhDs in physics, chemistry, and electronic science also. And we have different projects sponsored from DST, MNRE, DRDO, MIT, BRNS, various or industrial projects also. On that project, we required specific manpower. So for that project, we are also recruiting these BSc, MSc or specific people. So if you are interested to work in CMET, just follow our CMET website. Routinely, you try to visit once in a month so that you will get opportunity to work at CMET. So now let's move to our today's main lecture. So you know what is meant by spectroscopy. So the name itself defines spectroscopy is the branch of science that deals with the study of interaction of electromagnetic radiation with the matter. Very simple definition. Here, let me tell you that if your incoming radiation is one time and whatever outgoing radiation is there, you have to observe only two radiations. Based upon your observations, based upon your input, based upon your output, the spectroscopy technique is developed. For example, see, you are giving electromagnetic radiation having wavelength in the range of 200 to 800 nanometer. If you are striking this UV light on your matter, what kind of reaction is happening? What kind of radiation or interaction happens that you have to observe. Then this ray will reflect, diffract, absorb, or transfer that you have to measure. So based upon that, you can develop your own spectroscopy techniques. So in case of usable spectroscopy, the radiation having wavelength 200 to 800 nanometer, and you have to observe its absorbance or transmittance. This is a usable spectroscopy. You are giving X-rays and you are monitoring diffraction of X-rays is the XRD technique. If you are giving XPS, like that, the spectroscopy technique has been developed. Okay, just you have to monitor incoming ray, outgoing ray. You will get different technologies. Okay, so it is the most powerful tool available for the study of atomic as well as molecular structure and is used in analysis of a wide range of samples. So basically, there are two types of spectroscopy. One is atomic spectroscopy, the molecular spectroscopy. The name itself gives us idea about what is meant by atomic spectroscopy. It's concerned with the interaction of electromagnetic radiation with atoms are commonly in the lowest energy state called ground state. Okay. And in molecular spectroscopy, this spectroscopy deals with the interaction of electromagnetic radiation with molecules. Those who are interact with atoms is called atomic spectroscopy. Those who are interact with molecules is called molecular spectroscopy. So these basic things I have covered because for PhD you are working in some specific area. So just the refinement of your basic. So what is meant by electromagnetic radiation? That is the next question. What is meant by electromagnetic radiation? So electromagnetic radiation consists of discrete packets of energy called photon. Okay. A photon consists of oscillating electric field and oscillating magnetic field perpendicular to each other. See, here it is shown. See this wave propagating direction. So it is having some electric field as well as magnetic field, and that are mutually perpendicular to each other. So few basic terms you should remember, because if you are plotting any kind of graph, you should be very cautious for what is x-axis and what is y-axis. That is very important. For that purpose, you should know some scientific terms and how these scientific terms are being defined. Okay, so first term we are discussing about spectroscopy. Spectroscopy means what kind of wavelength or what kind of radiation or what kind of frequency that we should know. So what do you mean by frequency? It is defined as the number of times electrical field radiation oscillates in 1 second. You have seen previous slide, crust and trough, it's oscillating. So how many oscillations per second? That is called your frequency. The unit of frequency is hertz. 1 hertz is 1 cycle per second. This is very important term, wavelength. It is the distance between two nearest part of the wave in the same phase, that is distance between two nearest crest or trough. See here, this is the crest and this is the trough. The distance between two nearest crest or distance between two nearest trough is the wavelength of your radiation. So wavelength is generally it's described in angstrom. 1 angstrom is 10 raised to minus 10 meter. So now let's move to what is meant by molecular orbital theory. So in molecules, atomic orbitals combine to form molecular orbitals which surround the molecule. Okay. Any two atoms or atomic orbital combining together to form the molecular orbital. It's split in antibonding, non-bonding. Okay. The molecular bonds have lower potential energy than the separate atomic orbitals. This is the energy level of atomic orbitals. It comes together to form molecular orbital, so its energy is lower. Bonding and antibonding. Thus, the electron prefer to stay in molecular bond. This electron prefer to stay in the molecule. This is just basic concepts. So now let's come to our principle of usable spectroscopy. The principle is based on the measurement of spectrum of the sample containing atoms and molecules. Okay. What is meant by spectrum? It's generally graph. Okay. Spectrum is a graph of intensity of absorbed or emitted radiation by sample versus the frequency or wavelength. And the spectrophotometer is an instrument designed to measure the spectrum of compound. Okay. Spectrophotometer is nothing but its instrument. It contains your lamp, then gratings and detector. It's called spectrophotometer. So what is meant by absorption spectroscopy? So this is an analytical technique which concerns with the measurement of absorption of electromagnetic radiation. The UV radiation region extends from 10 nanometer to 400 nanometer, and the visible radiation region extends from 400 to 800 nanometer. So if you see the electromagnetic spectrum, wide electromagnetic spectrum, in that visible portion is 400 to 800 nanometer. And for invisible spectroscopy, we are seeing 200 to 800 nanometer for particular application. For dedicated applications, people are using the spectrophotometer, having its wavelength range from 200 to 3300 nanometer. That is called far UV region. So terms where terms depends upon the UV region. There are some UV regions. See, near UV it is 200 to 400. Far UV it's below 200 nanometer. For far UV spectroscopy is studied under vacuum condition. What is happening below 200 nanometer? Your moisture absorbs the UV light. Due to that, we should have some specific instrumentation. It should be moisture free or air free. Then only you will get the absorbance due to your compound. The common solvent used for preparing the sample is either water, or if your material is soluble in some organic solvent, then it will be alcohol or hexane or ethyl ester. You know the concept, like dissolve like. Your material is polar, then you will get polar solvent for solubility. If it is non-polar, you require non-polar solvent. And for material, there is another technique. In the next slide, we'll come to see for solid samples how to take the usable spectroscopy. So just see what are the heart of our absorption spectroscopy. There are two main laws, Beer's law and Lambert's law. So what is Beer's law? According to this law, when a beam of monochromatic radiation is passed through a solution of absorbing species, the intensity of beam of monochromatic light decreases exponentially with the increase in the concentration of absorbing species. In short, absorbance directly proportional to the concentration of medium. This question I routinely ask to our PhD student or any MSc students. So what is Lambert-Beer's law? So they are trying to explain this when a monochromatic beam of light, and we don't require this. We want a simple statement, absorbance directly proportional to concentration or absorbance directly to thickness. So what is meant by Lambert's law? Absorbance is directly proportional to thickness. See, Beer's law, it depends on concentration, and this is depends on thickness. All instrument thickness is constant, only we are varying the concentration. So combine Lambert-Beer's law. Absorbance is directly proportional to the path length and concentration of the medium. This is very important. Okay. Absorbance directly proportional to ABC. ABC This is here, sorry, this molar absorptivity, small a, molar absorptivity. I0 is the intensity of incident light. IT is the intensity of transmitted light. V is the thickness of the medium, which is constant, 10 mm, 1 centimeter. You are using this cuvette, quartz cuvette, that is same for all. This is the transmittance, IT by I0. If you take the ratio of intensity of transmitted light by intensity of original light, so this is called transmittance. If you multiply 100, it is percent. Absorbance is minus log of T. Minus log of T is your absorbance. Okay, now these are some basics about the various laws. Now we'll see what kind of various electronic transitions happens during usable spectroscopy. At room temperature, molecules are in the lowest energy level, E0. When molecules absorb UV visible light from electromagnetic radiation, one of the outermost bond or lone pair electron is promoted to higher energy state, such as E1, E2, or EM. It is called electronic transition. And the difference is delta E, means the difference from where this electron goes to higher, that the difference is En minus E0. En is 1, 2, 3. Okay. So delta E for invisible absorption study ranges from 35 to 71 kilocalories per mole. So these are various types of transitions happening during usable absorbance spectroscopy. First one is the what kind of transition? Sigma electron, pi electrons, n electrons. So these are the bonds happening in organic compounds. You might have remember your basic chemistry. So sigma electrons available in saturated compounds, pi electrons available in insaturated compounds, and n electrons, means non-bonding electrons, is available in non-bonded electrons. Okay, the possible transitions are sigma to sigma star transition, pi to pi star transition, n to sigma star transition, n to pi star transition, sigma to pi star transition, and pi to sigma star transition. This much transitions is being happening as per your supplied energy in the invisible region. So let's see one by one what kind of these transitions are there. So where the sigma to sigma star transition happens, sigma electron from orbital is excited to the corresponding anti-bonding orbital sigma star. The energy required is large for this transition. For example, methane. Methane has CH bond only and can undergo sigma sigma star transition and shows absorbance maxima at 125 nanometer. Okay, if you want to take the absorbance spectrum of methane, it will show peak at 125 nanometer. Because in sigma methane compound, carbon hydrogen, they have sigma bond. And this usable absorption spectroscopy shows sigma sigma star transition in the this absorption spectroscopy. So if you consider, you know how to calculate the band gap, which E is equal to H nu. If you solve that formula, E is equal to H nu, you will get band gap is equal to 1240 divided by wavelength in nanometer. If you put this wavelength 125, 1240 divided, almost 10 electron volt energy is required for this transition. It's big, how much large amount of energy required. Then pi star transition. Pi electron in the bonding orbital is excited to corresponding anti-bonding pi orbital. It's called pi star. Compounds containing multiple bonds like alkenes, alkynes, carbonyl, nitrile, aromatic compounds undergo pi star transition. Okay. Alkenes generally absorb in the range of 170 to 205 nanometer. Okay, it's as your wavelength increases, energy decreases because it is inversely proportional. Then N to pi star transition. Saturated compounds containing atoms with lone pair of electrons like oxygen, nitrogen, sulfur, and halogens are capable for this N to pi star transition. These transitions usually require less energy than sigma to sigma star transition. The number of organic functional groups with N to pi star peaks in UV region is small. 152 to 50 nanometer wavelength is required for this N to sigma star transition, because lone pair is available with oxygen, nitrogen, and sulfur. Then N to pi star transition. An electron from non-bonding orbital is promoted to anti-bonding orbital. Compounds containing double bonds involving heteroatoms such as carbonyl, nitrile, nitro undergoes this transition. The N to pi star transition is require minimum energy and shows absorption at longer wavelength around 300 nanometer. means its electron volt required is around 4 electron volt. Then another sigma to pi star transition and pi to sigma star transition. These electronic transitions are forbidden transitions and are only theoretically possible. Thus, n to pi star and pi to pi star electron transition shows absorption region above 200 nanometer, which is accessible to our usable spectrophotometer. The usable spectrum is of only a few broad absorptions. Whatever I explain now, this in one table it is shown. See here, this is n bonding orbital, this is pi bonding, this is sigma bonding. See, this is the energy. Okay, this y-axis is the energy. The electron from sigma bond to sigma star, it requires huge energy. Lowest energy required for n to pi star transition. Okay, this kind of transitions happens in organic compounds only. Now, let's see few more terms used in usable spectroscopy. So first one is the chromophore. Chromophore is defined as the nucleus of any isolated covalently bonded group responsible for absorption of light radiation. If you have some compound, the whole compound is not absorbing any visible region. Particular group is absorbing your radiation in that region. Any group which exhibit absorption of electromagnetic radiation in the visible or ultraviolet region, for example, CO bond or carbon-carbon or nitro group. Some of the important chromophores are carbonyls, acids, esters, nitriles, and ethylenic groups. So these groups are called as a chromophore, which is responsible for the absorption of radiations. See what kind of chromophores are there. So these chromophores, carbon-carbon double bond, carbon-carbon triple bond, carbonyl group, nitro group, and some halides, CX bond. Okay. So these are the excitations, n to pi star excitations happen here, and this is the lambda max for particular compound. And this is the molar absorptivity. Molar absorptivity means its capability to absorb the number of photons. So another term is auxochrome. So first we have seen chromophore, now auxochrome. So these are coordinatively saturated or unsaturated groups which themselves do not absorb radiation, but when present along with chromophore, enhances the absorption properties of the chromophore. So this, for example, if there are two friends and one friend don't want to go for a gym due to another friend he is going for the gym, collectively together both are going for the gym or doing some activity. That is the role of this chromophore gene. Presence of this, it is not absorbing, but due to its presence, it enhances its absorption capability. It's also known as color enhancing group. All auxochromes have one or more non-bonding pair of electrons like NH2, OH, OR, or COH2. For example, see benzene, its lambda max is 255. If you add OH group, it's phenol, it's absorbed 270. If you convert it to aniline, it's 280. See, absorbance increases by 15, here absorbance lambda max increases by 10 nano. Due to this group, what is happening? The absorption enhances. Then few more terms in usable spectroscopy: bathochromic shift, hypsochromic shift, hyperchromic effect, and hypochromic effect. So what this exactly? Due to presence of some groups, your UV light is shifted to blue or red. So we have to see what kind of effect is there, and this effect is due to what? Okay, so bathochromic shift means red shift. Your wavelength shifts to a longer wavelength. Hypsochromic, it shifts to the lower wavelength. Hyperchromic, hypochromic. Sometimes we are using why you are getting so much hyper. Hyper, its absorption intensity increases. Hypochromic, its absorption intensity lowers. So now this is about the basics of our usable spectroscopy, various laws, then various auxochromes or what kind of terminology we have seen. Now we will move to our instrumentation part. So what are the main components in the visible spectroscopy? Now everywhere there is a double beam source. photometers. Earlier, people are using single beam photometers. If you have seen colorimeters in your laboratory, that is single beam. Every time you have to put the solvent in that, you have to turn it either 100% or make it zero. Then you have to add your compound and check its absorbers or transmitters. But nowadays, double beam spectrophotometry is there. You have to do the baseline using that particular solvent, and then baseline, after doing baseline, you have to put your solvent plus samples so that whatever absorbance transmitters that is due to your compound. So what is the source? First source is there, then filters, monochromators, sample compartment, detector, and recorder. So here in visible spectroscopy, if you are trying to say UV visible spectroscopy, we require two types of sources, light source. So generally, visible spectroscopy, there are two labs, deuterium lab and xenon lab. Deuterium lab, its emission is 200 to 400 nanometer. And for xenon lab, it's from 400 to 800 nanometer. That's why we require two types of labs for the visible spectrophotometer. Then this is the slit, diffraction grating for making your light monochromatic. Monochromatic means very fixed. Then there are some filters, and see here, this is the mirror. It splits your incoming beam into two beams. One is reference beam and one is sample beam. Okay, before doing any kind of visible spectroscopy measurement, you have to do some baseline corrections. Whatever solvent you are using, you have to keep the solvent in both the cuvettes, reference beam and sample beam, so that it will nullify the absorbance due to your solvent. Using Western meter bridge, the signal received from the reference beam and sample beam, it nullified. So that next time you have to keep this cuvette same with same solvent, and you have to change this cuvette. So here we have to use some solvent plus sample so that you will get the absorbance or transmitter due to particular that your material. So this is the visible spectrophotometer we have at CMET. So its range is from 200 to 3300 nanometer, because we are doing some far UV measurements, so we required for solar cell measurements. Generally, most of the UV having wavelength 200 to 1100 nanometers. So that is sufficient for our day-to-day research work. So before that, we have to see here, this is sample compartment. This is the source here. It's, two lamps are there, deuterium and xenon lamp heated. And this side, we have the detectors. So in sample compartments, if you are doing your measurements from 400 onwards, you don't require quartz cuvette. Simple glass cuvette you can use for your measurements. But if you want to do your measurement at UV region 200 to 400 nanometer, you require quartz cuvettes, because quartz is transparent in this region. If you are putting glass cuvettes, it will absorb at 350 nanometer. Okay, so different types of cuvettes are available, ranging from 5 ml capacity to 0.5 ml capacity. What they are doing, for your 5 ml, the diameter is fixed, 10 ml. If your solvent is less, 1 ml or 0.5 ml, the path length is same, but from laterally they are making this very narrow, so that only beam from this side will go. So path length is same, 10 mm, but lateral distance they are using, so that cuvettes available in the market from 0.5 ml to 5 ml. So now, okay, this is about our basics about instrumentation part. Now we'll move to our the application part of usable spectroscopy. So that is very important. So what is the basic applications of invisible spectroscopy? First one is the detection of impurity. So let me clear, we should have the some information of your sample, or we have to take the help of some another instrument or another characterization facility. Then only we can identify the particular compound. Single characterization technique or single instrument will not provide you any kind of analysis. Okay. If you want 100% analysis, or you want to know the perfect name of that impurity or what is the compound content, you require IR spectroscopy, invisible spectroscopy, NMR, GC. Okay, this is about our organic compound. If we want to identify the inorganic compounds, We should have XPS, XRD, usable spectroscopy, SEM, TM, EDX analysis. Using collective information from all the instrumentation, we can identify particular compound. If you are saying, I want to identify this compound from usable spectroscopy, we cannot help you. We should have a particular kind of information about your compound. Okay. Otherwise, we have to take the help of two, three techniques. So here, first detection of impurities. So here, what is the usable spectra of cyclohexane plus benzene impurities there? And whatever solvents or compounds coming in the industry, we have to check its purity. So this is the very simple usable spectrophotometer. Using these, you can identify the type of purity. If there is no impurity, single peak you will get. If there is impurity, you will get two, three peaks. Number of peaks means number of impurities. So detection of impurities, invisible absorption spectroscopy is one of the best method for determination of impurity in organic molecules. Additional peaks can be observed due to impurity in the sample, and it can be compared with the standard raw material. So here, benzene appears as a common impurity in cyclohexane. Cyclohexane, see, this is the benzene. This peak is due to the benzene. If you are getting two peaks, means you can say there is two compounds. If you have pure benzene, pure cyclohexane, you take the usable absorption spectra of these two peaks and then compare this with the mixture. You will identify, yes, this mixture probably due to this benzene or due to cyclohexane. Another one is structure determination of organic compounds. For MSc Organic Chemistry or MSc students, they have famous structure identification problems for your exams. Using UV visible, FTR, and NMR, you have to identify the structure of the compound. So in this case, usable spectroscopy is useful in the structure determination of organic molecules, the presence or absence of unsaturation, presence of heteroatom. Okay. From the location of peaks and combination of the peaks, it can be concluded that whether the compound is saturated, unsaturated, or heteroatom present or not. This is from usual absorbers. You know that earlier slide we have some also grown or what kind of compounds are there that can be identified. Another application is qualitative as well as quantitative analysis. If you know what is the compound is present and you want to find its concentration, the concentration we can identify using spectroscope. But for that purpose, you should know what kind of compound is there. So this, I think, for BSc or MSc, this kind of experiments are there. They are making some cobalt or copper solutions and making one unknown concentration. So for this purpose, what one has to do? One has to do standard samples and take its absorbance. Unknown sample, you take its absorbance and you plot the standard plot. And corresponding to that absorbance value, what is the concentration? So that concentration can be identified. But for this purpose, you should have the knowledge of that compound. If the compound, if you don't know the compound, then you cannot use this technique. So one of the application, qualitative quantitative analysis using in-vivo spectroscopy. So here see the different compounds showing usable absorption spectrum, absorption maxima is different. So this is very important for identifying some impurities or content of our compound in other compounds. Another one is chemical kinetics. You can study the chemical kinetics using invisible spectroscopy. So here, what I have shown here, this is the invisible absorption spectra of methylene blue dye. So what we did, we are doing some photogalactic dye digestion. So here, this is the methylene blue absorption spectra, 10 ppm. So it's showing absorbance at 2. It's x-axis is 664 nanometer, y-axis is absorbance 2. So here, what is happening? With the progress of reaction, this methylene blue dye get degraded. Okay, I am using word here degrade. It means some molecule, if structure is there, some compound is getting out. That is called degrade. Okay. So after 15 minutes, absorbance going down, 60 minutes, 120 minutes, is almost 70 to 80% decompose or degrade. So using this absorbance value, with the time, we can study its chemical kinetics. Rate of reaction can be studied. Okay. So this is what we did. We converted this percent dye remaining versus time, and we observed that this material is prepared, zinc oxide is prepared, and we studied its catalytic degradation studies. So here what we observed, this material prepared at 8 hours is having highest degradation. Using this chemical kinetics, we can identify which material is best. So here activity trend observed is 8 hours is the best, then 12 hour, 2 hour, and 4 hour. So this is the chemical kinetic study. I am doing this reaction at my laboratory at different temperature and light intensity is different. And I want to compare my data with earlier data or with some other scientist data. So we should have some figures or numbers. So for that purpose, if you plot this LNC by CT versus time, and the slope of this graph gives us rate constant value. And this rate constant value, you can compare this. See here, whatever zinc oxide prepared at 2 hours, its rate constant is 1.22 into 10 to minus 2 minute. This rate almost become 3 times more, 3.73 into 10 to minus 2. Or this rate I can compare with earlier other scientists' data. So this kind of study can be performed using invisible spectroscopy. Okay, so what we did, we just studied its absorption spectroscopy with time, then we find out its percent degradation, and then we converted this data into LNC 0 by CT versus time. This is standard pseudo first order reaction, and the slope of this graph gives us rate constant value. So this is very important data we are getting using usable spectroscopy. And if you don't have usable spectroscopy, using any kind of colorimeter, you can identify this kind of chemical kinetics. Another one is pre-radical catalyzed reactions. So this what happened in earlier days. We are doing this kind of reactions. We are converting this cyclohexane into alpha bromocyclohexane using NBS under light. So people have reported this kind of reaction at 100 degree, 3-4 hours. So we developed this under invisible light. So here what happened? This cyclohexane, we are putting some N-bromosuccinimide. You know that NBS short. N-bromosuccinimide is free radical. It generates free radical of Br. And within a light, within 0.5 to 17 minutes, it is giving this kind of compound. So we submitted this paper to tetrahedron later. So that the reviewer accepted all the things, but he asked us, you prove this reaction is free radical catalyzed or not. So we observed the big trouble at that time, how to prove this reaction is free radical or not. Because NBS is free radical, it creates free radical, everybody knows, but how to prove it? Then one another person is working on DPPH radical. DPPH radical. He said, it's very simple. You take the invisible absorption spectrum of DPPH. Okay, this is the absorption spectrum of DPPH. And then while this reaction, you put the 2-3 drops of this reaction in DPPH, whatever the radicals that are being trapped in the DPPH. Okay, so that is called trapping of radical reactions. So we did it, and using usable spectroscopy, this peak diminish. This DPPH radical comes down. It indicates that DPPH react with this PR radical, and the radical is consumed. So this very informative technique we use for showing our reaction, this particular reaction is free radical catalyzed or not. So immediately this spectra is being absorbed, accepted by reviewer, and our paper get published. So this is very important. Use of spectroscopy is important to design the reaction pathway of your materials. So another one is the application is the band gap of material. So those who are working in the materials or semiconductor metal oxides, metal sulfides, or graphic carbon nitride, this is very important terminology for them. Okay. So before this, let me tell you what is meant by band gap or how the material is being classified based on the band gap. You know that metal have valence band, conduction band, but this bands is overlap. There is no gap between this band. In semiconductor, this gap varies from 0 to 3.5 electron volt. And if this band gap is above 3.5 electron volt, that is called insulators. Okay. So based upon the band gap, this material can be classified as metal, semiconductor, and insulator. For metals, there is no band gap because conduction valence may almost overlap. Semiconductor up to 3.5 electron volt. There is no hard and fast separation between semiconductor and insulator. But few people are saying, okay, above 3 electron volt, it is insulator. Few are saying above 3.5, it is insulator. But there is no hard and fast boundary. But we are, for our convenience, we are saying up to 3.5 electron volt. So how this change in the band gap of the material shows invisible shift. See here what is happening. Many of you are must be making some nano material. So your material converted from bulk to nano, or had you really prepared the nano material that can be easily identified using usable spectroscopy? You just see its usable spectra. It is showing blue sheet means your material is nano. Okay, that is the basic identity to identify your material has become nano or not. So how this usable absorption spectroscopy shifts towards the blue side. Okay, this is the basic concept behind this. So here what is happening in bulk structure, all semiconductors, valence band and conduction band. And the distance between top of the valence band, the bottom of conduction band is band gap. Okay, just see the clear-cut definition. I am saying top of the valence band, the bottom of conduction band. It's called band gap as area. Okay. So here what is happening? If you change this bulk material to nano material, this band becomes more and more discrete. Okay. So the distance travel this electron from top of the valence band to bottom of conduction band getting increases. And due to this increase in distance, you require higher energy. Higher energy means wavelength should be lower. This is the reason why usable absorption spectroscopy shows blue shift if you change your material from bulk to nano. Okay, so this is the scientific definition of our band gap. The band gap generally refers to the energy difference between top of the valence band and bottom of the conduction band. You have to mention this top of the valence band, bottom of the conduction band. And in generally, in semiconductor physics, the band gap of semiconductor is always two types. One is direct band gap, another is indirect band gap. It's for your convenience. You are coming to the college or coming to the school or your laboratory from home directly. You are coming to your lab. That is called direct band gap. If you are going to your friend's home, sitting there collecting, it's called indirect band gap. So what is exactly happening here? If you shine the light and the electron from valence band directly goes to the bottom of conduction band, it's called direct band. But in certain materials, this top of the valence band and bottom of the conduction band is not well aligned. It is slightly shifted. So here, this electron has to change its vector momentum. It has to change its direction to go to the lower of conduction band. So that is called indirect band gap. Electron has to go and then he has to change direction to go to the bottom of the valence band or conduction band. Okay. So this is the basic difference. If you are going any kind of interviews, material related interviews, people will ask you what is the band gap. If you answer it, then you will next question, what is direct, indirect, how to identify it. That is the basic questions. Okay. So in case of visible spectroscopy, what is happening? We have double beam spectroscopy. We are transferring our reference beam as well as from sample compartment. So here what is happening? What your material is there, it absorbs, and remaining material is transported to your detector. And from here also, one beam is going to the detector. So if you transfer 100 photons, from reference beam 100 photons are coming, and from sample beam only 50 beams are coming, 50 beams are getting absorbed, transmitted or diffracted. But your detector what will say, from here 100 is coming, from here 50 is not coming, means only 50% get absorbed. In case of solid samples, what is happening? If you disperse these solid samples in the solvent, what is happening? Your live beam get reflected, absorbed. But your detector will say everything get absorbed. So for measurement of visible spectroscopy of solid sample, you require different kind of accessory. You cannot simply put your material in the liquid, disperse, sonicate, and take its visible spectra. It will give you some wrong information. For getting correct absorption behavior, you have to use diffuse reflectance kit. Here, what is happening? In that case, incident beam comes on your surface and it reflect all directions. And detector is at the top and bottom your that kit. and it measures total reflected light. And using Kubel-Monk function, you have to convert its reflectance into absorbance. That is the perfect absorbance of your solid sample. And using this solid sample usable spectroscopy, we can identify the band gap of your material. So here, what is meant by diffuse reflectance spectroscopy? See here, light cannot penetrate solid samples. It is reflected on the surface of the sample. Incident light reflected symmetrically with respect to the normal lines called specular reflection, while incident light scattered in different directions is called diffuse reflection. So here, this is the solid sample attachment. Here, this is the sample, and this is the reference. Everywhere we require reference, okay? Without reference, we cannot do anything. So for solid sample, we are using barium sulfate as a reference. So here one solid cuvette is there, it is containing barium sulfate, and here your sample, you have to fix these two samples first, barium sulfate. You have to analyze your material, you have to do the baseline correction so that your absorbance due to this material is getting nullified. Later on, you have to keep your sample here, and with respect to this sample, it will show the reflectance. And from this converting your Kubel-Monk function, you will transfer this reflectance value into the absorbance value. And using that absorbance value, you can identify the band gap of your material. So this is the specific attachment it comes within usable spectrophotometers. Okay, now we have taken the diffuse reflectance spectrum of cadmium sulfide. If you are taking it dispersed in the liquid and you are taking the spectra, it will not come correctly. It will give you wrong information. But if you can get this DRS spectra of cadmium sulfide, you will get this kind of nice picture. And roughly, absorbance versus wavelength. If you put the tangent on both the axes, where it means 520, and this is the band gap formula. 1240 divided by wavelength in nanometer. This comes from E is equal to h mu. If you solve this equation, E is equal to h mu, you will get this kind of formula, 1240 divided by this wavelength in nanometer. See here, 1240 divided by 520. This 520 is from here. Band gap is 2.38 electron. But this is not the authentic way to calculate the band gap. We have to plot the tau plot. Okay, tau plot. Using tau plot, you will get this kind of band gap. But roughly, it is giving idea what is your band gap value. See here, one material, pentacene. This is organic compound. So let me tell you the different transitions happening in organic compound as well as inorganic compound. In inorganic compounds, the transition happens from valence band to the conduction band. And due to that transition, we are getting absorbers. In organic compound, N star, N pi star, sigma star, that transitions happens. This is difference between organic semiconductor and inorganic semiconductor. So here, pentacene quinone, we have taken this pentacene quinone's absorber spectra in the solvent. Okay, because pentacene organic solvent, it is soluble in some acetone or something it is. Then we have converted this absorbance into tau. Tau plot means what? Alpha h nu square versus wavelength in nanometer. If you convert this whole axis 1240 by this wavelength, you will get this values in the electron volt. And here this alpha h nu square. Alpha means your absorbance, h nu means this. You convert it into, you can develop this in Excel also. You have to put the formula. You will get this alpha h nu square versus wavelength in EV. Just plot the tangent, you will get this is the exact value of your band gap. See here, from band gap, we are getting 2.76. From tau plot, we are getting 2.82. So this is more authentic, is near to theoretical band gap. So this is the exact formula of tau plot, alpha h mu. It's alpha h mu square or square root of alpha h mu. It's A in bracket h mu versus EG is band gap. Means plot of product of absorption coefficient and photon energy versus photon energy. Okay. If you plot h nu versus alpha square, forms a straight line. It's referred as a direct. If square root forms a straight line, then it is indirect band. Okay. If you see TiO2, ZNO, molybdenum sulfide, bismuth sulfide, they are direct band gap as well as indirect band gap. See here what we did, we used this usable spectroscopy to observe the change in the band gap of materials. Here what we did, we doped vanadium in TiO2 lattice. Okay, so here this is this black one is the usable spectra of our TiO2. This dotted line is the spectra of our vanadium pentoxide, V2O5. See, is the difference. As you increase the vanadium doping in TiO2 lattice from 0.001 to 20 mole per cell, see this invisible spectra, how nicely it sits. It can cover whole solar spectrum for your photovoltaic analysis. So using this invisible spectroscopy, we can check the absorption profile of our material and we have the idea of our band gap of the material. So here you may think that how this band gap shifts. Here what is happening? The TiO2 has some kind of conduction environment. Its position is fixed. What we are doing, we are inserting the 3D level of vanadium in between. It's near to 3D level of TiO2. So this electron has to go from here to here. Okay, not here. So it requires less energy. Less energy means higher wavelength. That's why it is showing this kind of shift in the usable spectrum. So this is very important. Band gap we can check using usable diffuse reflectance usable spectroscopy. Another one is that in using usable spectroscopy in DRS mode, we can identify whether the compound is single phase or multi-phase. Okay. See here what we did, we prepared zinc oxide and cadmium sulfide. You know that cadmium sulfide visible light active is showing absorbance in 530 nanometer for bulk material, and ZNO showing absorbance at 380 nanometer. So two compounds here, ZNO showing absorbance at 380 nanometer. As we loaded cadmium sulfide on zinc oxide, varied from 0.1 to 5 moles. Here we are getting absorbance due to this cadmium. See, the absorbance is in between 400 to 500 nanometer absorbance enhances. Why this absorbance enhances? This is due to the cadmium sulfide. See here, this zinc oxide is showing single peak like this, but here we are getting some steps up to here Zn and then this cadmium sulfide. But this intensity of this cadmium sulfide or Zn depends upon your molar absorptivity. Based upon intensity, you cannot judge the percentage of particular compound. Like in XRD, we can identify whether this compound is 30% or 20%. But in case of UV, it totally depends upon your molar absorptivity. Because if you are having cadmium sulfide on both the material, if you are striking 100 photons, may not 100 photons get absorbed because cadmium sulfide is having higher molar absorptivity. It will absorb maximum photons, but zinc oxide not. That's why here, even though it is 5 mole percent, it is showing almost 90% absorbance as compared to ZnO. But here, what we are getting basic information, we are getting two types of curves here. So maybe it contains two kinds of material. This is due to CDS and this is due to ZnO. I know I put it CDS, that's why I know this is due to CDS. So already I told you that without any information, we cannot tell you something about the material. So this kind of important information we are getting using spectroscope, okay, in solid mode. So another what we did, we prepared some graphitic carbon nitride Ti3C2TX nano electrostructures. So here, magazine is like a metal, okay. So here we are getting absorbance here at 700 nanometer. This is due to surface plasmon resonance. In case of metals, what is happening? These electrons are vibrating on the surface, and due to that vibrating electrons, it interact with the usual electromagnetic radiation, and it is showing absorbance. You know, in semiconductor, what is happening? Absorbance due to absorption of that electromagnetic radiation. This electron goes from valence band to conduction band. Due to this, the absorbance happens. In kind of nanomaterials, due to surface resonance, we are getting absorbance. So here, see this absorbance is getting at 700 nanometer. So here we initially we thought this is due to semiconducting nature, but later on after getting the literature, we came to know that this is not due to the semiconductor behavior because a magazine, this particular magazine behaves like material property, metallic properties. But here what we did, this is the graphic carbon nitride. It is showing absorbance around 420 nanometer. And we prepared this composite, varied from 1% to 0.05%. Okay. So here, as we change this percentage, see this graphitic carbon nitride absorbance getting nullified. It's there. But this covers whole your absorption spectrum. So using this, we came to know that yes, this absorption profile is at 700 nanometer and here at 420 nanometer. We can use this kind of light for our reactions. So to exactly identify the band gap values, we plotted the tau plot, alpha H mu square versus electron hole. But for composite kind of view, this you cannot say the lowering of band gap or changing the band gap because this is a mutually paired. One molecule have this kind of band gap, another is have this kind of band gap. So there is electronic transition. So combined band gap you cannot identify. So you have to just we're getting some kind of information about the band gap. And this proves that your heterostructure has been formed or not. For that purpose, we are analyzing here. See here, what for what purpose we are using this technique and what kind of interpretation you are gaining, that is very important. Another case, what we did, we prepared here tungsten oxide nanostructures and heated from 200 to 800 degrees centigrade. From XRD, we saw that there is a monoclinic phase, triclinic phase, one more phase is there. But here, visible spectroscopy also gives you different absorption profile for same material with different structure. Okay. See here, this at 200, it is tungsten, hydrated tungsten oxide. So it is showing absorbance at 300 nanometer. But as you heat from 400 to 600 to 800, its chemical nature changes as well as structure associated. At 400, it completely transforms into WO3. This is hydrated. Now this is WO3. All three are WO3, but it is having monoclinic phase, this is having triclinic phase, this is having another phase. You change its crystal structure, you are getting different absorption behavior. Means without taking XRD, you using usable spectra, using its bandage, its band gap or absorption profile, you can identify particular compounds structure. Okay, another what we did, we prepared this TAL at different temperatures and different reaction time. So here what happened? We prepared this tea out at 24 hours, 48 hours, 150 degree, 48 hours, 180 degree, 48 hours, 200 degree. But from the visual absorption spectra, we're getting different kind of absorption behavior in the 400 to 700 nanometer. It shows some extended absorbance in this region. And this must be beneficial for your photo-related reactions for application point of view. So here we try to identify why this absorption behavior is different in this case. So we found that in this case, some kinds of nitrogen is getting doped in TiO2 at oxygen place. Due to that, we are getting this enhanced absorbance in this region due to formation of TiO2 minus X and X. Okay, so using this, we are getting change in this band gap, okay, of TiO2. Another one is here, the material is same. Here what we did, we prepared the TiO2 using sol gel technique and we heated this from 400 to 800 degrees centigrade just to see what kind of structural behavior is happening in this TiO2 and what is its change in the optical properties. So here what we observe, up to 500, the anatase phase is stable. Anatase at 25. If you heat it at further, the small peaks are arriving at 27. So this is the rutile phase. This anatase phase start converting into rutile phase. And this anatase phase has band gap around 3.2 electron. See here 400 and 500. So band gap is lower than this 3.2 electron volt. And if you convert this anatase into rutile, it shifts to a higher levels. So this band gap due to the rutile phase. Means from illegal spectroscopy, your material is anatase or rutile, particularly for TiO2, you can get the knowledge of band gap using this DRS visual spectroscope. Another one is that is all about our material related identification. Okay. So that we are routinely doing at our laboratory. Another general application is identification of fat content in the milk. You have to take the absorber spectra of the milk, and then as your fat content decreases, its absorption is also decreases. So if you know that this milk contain maximum fats, its absorption should be more. If it is going down, means your water or some additive must be there. Another that is already I have discussed, the formation of nanomaterials has changed in the band gap of the material. So this is the famous cadmium telluride materials. And see this the bulk material. If you change this material from bulk to nano, see how the change in the band gap appears, and it covers whole solar spectrum from 400 to 700 nanometer. It covers whole solar spectrum. This is the beauty of your nanotechnology. You can your material is same cadmium telluride, but you can make this material in that way so that it can absorb whole solar spectrum. Okay, that's all about the usable spectroscopy. Now, I think we'll discuss the questions related to usable spectroscopy, then we'll go for our photoluminescence spectroscopy. So now the session is open for discussion. Hello, audience are there or left? So Iris, our students, if you have any queries, you can ask me. Otherwise, we'll go for next photoluminescence spectroscopy lecture.
हाँ सर क्या म्हणता
Sir, we'll discuss related to usable spectroscopy. If students have some queries or questions, we'll discuss. Otherwise, we'll go for photoluminescence spectroscopy lecture.
Students are requested to post your questions in chat box or question answer section if you have any question. Chat box open आहे. Questions post करू शकतात.
I think students don't have any kind of questions. So can we go for our next lecture?
Yes sir, please proceed.
Okay, so if there is no question related to usable absorption spectroscopy, then we'll move to our next topic, photoluminescence spectroscopy. Now we have seen the absorbance, now we have to see the emission. Whatever you have gained from my lecture, now I will ask you the questions related to emission. That is the way. Otherwise, you will not absorb anything. What kind of emissions you are showing, that I would see now. Okay. Are you getting? My voice is clear?
Yes, sir, you are audible.
Okay, now let's see the introduction to luminescence spectroscopy. So material that emits light is called luminescent material. Okay. You know there are some, the famous radiums. If you shine the light on radium, it is emitting some light. So you know that some red, white, or yellow colored radiums. So this is called luminescent materials. Okay, emission of light by substance caused by chemical reaction, electrical energy, some atomic motion, or stress on crystal. Okay, this emission can be caused by many ways. Okay, first one is chemical reactions, some electrical energy, then some atomic motions or stress. There are some mechanoluminescent material. If you touch that material, it will start illuminating. That is called mechanoluminescence. Here we are seeing optical emission. Luminescence is the emission of light by certain material when they are relatively cool. So this is the various terminologies or how the many scientists or people have defined what exactly luminescence means. Greek word phosphor is used to describe luminescent nature. It emits energy from excited electronic state as light. The wavelength of emitted light is a characteristic of luminescent material. The emitted light carries material signature. Okay, this is important. Last sentence is important. Emitted light carries material signatures. Okay. And the wavelength of emitted light is characteristic of luminescent material. They are giving some particular information to us. What kind of this material is there, and what kind of information we require from this. So you should know what kind of information you want to grab from that particular technique. So there is various types of luminescence. Photoluminescence. Basically, we are seeing this photoluminescence only in that fluorescent and phosphorescence. Then thermoluminescence is there, electroluminescence is there, cathodoluminescence, and triboluminescence. Activated by, first one is by light, second one is by heat. If you heat the material, it will get luminescent. Many of the people are heating their material with the furnaces. If you make the temperature of furnace around 700, it gives red colored emission. That is thermoluminescence. Then electroluminescence due to flowing of electrical current, cathodoluminescence due to cathode ray, and triboluminescence due to friction. We can say this mechanoluminescence. If you press some material, it illuminates. Okay, so these are the basic many types of luminescence. Out of that, we are seeing this photoluminescence. So what is meant by photoluminescence? Okay, the phenomenon of temporary light absorption and subsequent light emission is called photoluminescence. You have to absorb that light and again you have to emit that light. The emission we have to see that is called emission. Photoluminescence is a process in which molecule absorbs photon exciting one of its electronic to higher electronic state and then radiates a photon as electrons to the lower energy state. Okay. Means this electron is absorb the energy, it is going to excited state. From excited state, it has to come back because if you are having higher energy, you are unstable. You cannot stay at that level. You have to emit some energy and you have to come ground state. That is the basic phenomenon, basic concept. And whatever this you are coming, where you are coming, and how much light you are emitting, that is the measurement of that is called photoluminescence. Forms of photoluminescence. Luminescence after absorption are fluorescence, shorter time, and phosphorescence is longer time. Means if you want to go home immediately, that is called luminescence. Few students, like that I said, they are not going home or not coming to the lab immediately. They are going to their friends' home. They are sitting there and then going home. That is called delayed luminescence. That is called phosphorescence. So these are the three main processes happening in photoluminescence, any kind of photoluminescence: excitation, relaxation, and emission. Okay, first one is excitation. Particular energy of light, if you strike on material, this electron or molecule absorbs the light, it goes to the higher electron state. They are having higher energy and they are unstable. They have to come back. While coming back, they are emitting light. Now, this light is called emission. Okay. So these are the various list of material. They are showing fluorescence and phosphorescence. Only the term you have to keep in mind. Fluorescence means immediate emission. Phosphorescence delayed emission. See here, vitamin B2, tonic water, highlighter, pyranine, banknotes, postage stamp, credit cards, petroleum, uranium glass, rock salt, fungus, athletic boots, canola oil, some postage stamps having certain kinds of fluorescence material. Okay, see these pictures are present. Many of the if you are athletics, your shoes are having some kind of fluorescence material, t-shirts having fluorescence materials. Then typically aromatic molecule shows phosphorescence like quinine, fluorescein, rhodamine B. This is the famous dye we are using for dyeing. So this one is fluorescence. Then this is organic semiconductor, coumarin, acridine orange, some minerals, materials in low dimension, glass in rare earth science. Material low dimension means either zero dimension or two dimensions. Generally, nanomaterial classified in four dimensions. Zero dimension means it is quantum dots having size below 5 nanometer. If it is wire-like structure, it's one dimension. If it's two dimension, means it's mobile or page-like structure, two dimension. Three dimension means cubic structures. See, this is the famous Jablonski diagram you might have learned during your BSc studies. Here, what is happening? See, this there are various density states. The electron from S0, 1, 2, 3, from where it is getting excited, we don't know. So that's why we're getting bulk spectrum. Here, the particular energy of light absorbed by the cells electron goes to the excited state, and while coming, it emits the light. So that is called fluorescence. So here, what is happening? This diagram gives us information about your electromagnetic emission spectrum. So if it comes within the molecule, it is called singlet transition. If it is going to another molecule or another density of state and coming down, then it's called triplet state. It's singlet to triplet state transition. So let's see what is meant by fluorescence versus phosphorescence. So phosphorescence is always at longer wavelength compared to fluorescence. Phosphorescence is narrower compared with fluorescence, and phosphorescence is weaker compared with fluorescence. So in general, quantum will define as number of photons emitted divided by number of photons absorbed. If you are giving particular emission spectra related to your compound, you have to give the photoluminescence in terms of quantum yield. If you are striking 100 photons, out of 100 photons, how many get absorbed? That the ratio is called quantum yield of your spectroscopy. So these are the general uses of photoluminescence spectroscopy. So here at CMET related to material research, we are trying to identify emission behavior of our material. So photoluminescence is an important technique for measuring the purity and crystalline quality of the same metal. If your material is highly crystalline, you are not getting any kind of delayed emission. You get sharp emission peaks. That is called your material is of good quality. Using time-resolved photoluminescence, one can determine the minority carrier lifetime of semiconductors like gallium arsenide. Here, there are two types of photoluminescence spectrum. One is in the range of 200 to 800 nanometer, that is normal photoluminescence. Another one is having far higher region, it is up to 1500 nanometer. Another one is time-resolved photoluminescence spectroscopy. So in that case, after exciting with a particular light, how much time your electron hole are getting remain. So that time also we can identify. So using that time, you can identify the reaction kinetics of your particular reaction. Can be used to determine the band gap, exciton lifetime, exciton energy, by exciton of semiconductor and other functional materials. It determines the properties such as structure and concentration of emitting species. Other uses are recombination mechanism can be studied of excited electron pairs, materials quality, quantum yield, and transition time. So these are the instrumentation major components. This is particularly for the normal spectrophotometers. It's available with all major laboratories. It ranges from 200 to 700 or 800 nanometer. So here the illumination source is generally xenon lab. It's 150 watt xenon lab generally many instruments having. For a particular reaction, if your emission wavelength is up to 1500 nanometer, they are using some lasers. Some lasers have been there to excite the particular nanomaterials. Then light delivery system, there are again lenses, mirrors, optical fibers, and gratings are there. Wavelength separators are there, both monochromator, excitation, emission, and detector is generally PMT, photomultiplier, same as the usual spectrophotometer. There also a detector is PMT. So now see, this is about the basics of the photoluminescence spectroscopy. Here, now we are covering some materials, but we have synthesized at our laboratory. So here what happened, we prepared zinc oxide as I have shown in the usual spectroscopy of chemical kinetic studies. So here what we did, we prepared this zinc oxide at 2 hours, 5 hours, 12 hours, 48 hours. Material is same, only we change its reaction time. Even its temperature is also same, only reaction time varies from 2 to 48 hours. See what happened. SEM, we see that the length of the rods is a few nanometers. As we increase it 2 hours to 5 hours, it is up to few hundred nanometers. Then it is 500 nanometer. And at 48 hours, it's micron size. Length of rod becomes micron size. So to check its optical properties, usable spectroscopy, we got 372 absorptions. But here PL is in PL, what is happening? Zinc oxide band gap is around 3.2 electron volt. It is showing bandage emission. Bandage emission means what? This is the band gap. This is the valence band. This is conduction band. The electron goes from this to this and again coming back here. It's called bandage emission. So here we got two peaks, 390 nanometer bandage emission and 500 nanometer. This is due to the defect created in between this zinc oxide. So what is happening? Due to this, what is happening? The electron from valence band go through the conduction band. Few electrons coming back directly, few are staying here. It's get transferred to here. Okay. And there may be some zinc vacancies or oxygen vacancies. That is debatable issue. The 500 nanometer peak is due to zinc vacancies or oxygen that is not related confirmed. But there is some particular vacancy or defect. At that point, this electron goes getting transferred. And due to this transfer, we are getting peak at 500 nanometer. Because see, 500 nanometer, how much energy required? You will put it at 500 nanometer, 2.5 electron volt. This is 3.2. This is something 2.6 electron volt. If your electron comes from here, equivalent energy is emitted. That is called 500 nanometer emission level. So here, what is the beauty? We prepared 2 hours to 48 hours. We created certain kind of defects in the zinc oxide. And the defects were getting enhanced emission at 500 nanometer. So this zinc oxide material is same, only your reaction time is varying. You can use this material for fabricating green light emitting diodes. Okay, so this particular information we get from photoluminescence spectroscopy. Another one, I have shown you that zinc oxide we loaded on cadmium sulfide is DRS spectra. Cadmium sulfide showing much more absorbance as compared to zinc oxide. And two phases were identified there. Okay. So in case what is happening, we loaded this cadmium sulfide on zinc oxide nanostranges. So they are showing coupled catalytic systems. So here what is happening? Both the material absorbs electron photons. Okay. And at the same time, what is happening? The electron from zinc oxide, conduction band electron from zinc oxide, react with holes in the cadmium sulfide. At the same time, this electron present in conduction band of cadmium sulfide is available for photovoltaic reactions. Is here what we did, 50% electron hole we sacrifice. At the same time, 50% we use for our reaction. So this is the beauty of this coupled catalytic system. So here what is happening? See, this transition is getting lowered. Means the electron from this to this is not coming directly here. Okay, that's why it is bandage emission is going down, and this also going down. This minimizing intensity tells us that there is an electron transition from one conduction band to another conduction band, and it gives us photovoltaic activity. So based on this PL, we draw this mechanism and we could able to publish this pattern. Another one is the size dependent PL of CDS. PL also tells us the information about the particle size of your nanometer. So this is the cadmium sulfide, is the bulk material, this absorbance around 480 nanometer. If you make it lower size, it's around 480 nanometer. So the change shift in the PL emission peak. So this is, if you see the emission spectra of bulk CDS, you will get PL emission at 550 nanometer here. Both these materials are narrow, but its particle size distribution is very narrow. 50 nanometer particles are there. See, this is ranging from 50 to 500 nanometers. So here, change is clearly observed using this photoluminescence spectroscopy. Means absorption, here what is the emission maxima? You can identify emission maxima, and from that you can say your material is narrow. Using this full width at half maxima, we can also identify the particle size distribution of your particular material. Okay, that's all about the photoluminescence spectroscopy. Because this much material we are analyzing using photoluminescence spectroscopy. And once again, I would like to thank the organizers for giving me opportunity to present my work here. Now, I will be happy if you have any questions. Hello.
Yes, sir.
Sir, now the lecture is closed. Now the session is open for discussion, sir.
Okay. So again, participants are requested, if they have any queries, please ask in the chat box or question answer section. I think everyone understood the concept clearly, sir.
There are only two things, whether percent absorbance or 100% emission.
Yes, yes.
I think all the students are sitting in one class or individually they attended. Because I could see here only three logins, mine one, Yogita, and your college.
We are panelists and students are in attendee.
Okay, okay, okay. Okay, if you have any question, please share my email ID to them, sir, so that they can ask me later on also.
Yes, sir. Yogita madam.
Thank you, sir, for your valuable lecture. We understand it better more. Thank you, sir.
Thank you for the organizers. Thank you, Iris, sir. Shall I leave now?
Yes, sir.
Okay, thank you.
Okay.
Thank you, sir.
Thank you.